Beyond the reach of the last star, where light grows weary and time itself thins to a whisper, there is a darkness so profound it feels infinite. A silence that does not merely exist, it reigns. Here, in the cold cathedral of the cosmos, lies what humanity once called nothing. For centuries, this void was thought to be the ultimate absence, a perfect vacuum, stripped of all matter, all energy, all possibility. A hollow stage on which the universe's drama might unfold, indifferent and inert. But the deeper science has peered into that blackness, the more the void has begun to shimmer. Not with light, but with suggestion, restless fields unseen, forces, and a constant, ghostly murmur of creation and annihilation. The perfect vacuum, it seems, is neither perfect nor empty. Quantum theory whispers that even here, space is not still. It seethes with ephemeral particles that burst into being only to vanish an instant later, like the heartbeat of a hidden world. The emptiness is alive, its surface tension holding the architecture of reality itself. Yet in this hidden life there is danger, for if the vacuum is not what we think, if it is unstable, volatile, or transient, then all of existence rests upon a knife's edge, balanced atop the restless dreams of nothingness. What lies inside the perfect vacuum is not absence, but perhaps the most powerful, mysterious, and dangerous entity the universe has ever known. The human story of the vacuum begins not in a laboratory, but in the mind. For the earliest philosophers, nothingness was a thought too unsettling to embrace. In ancient Greece, Aristotle declared that nature abhors a vacuum. To him, the void was not merely empty, it was impossible. A cosmos without substance would collapse upon itself. Between every star, every planet, and every breath of wind, there must be something, an invisible plenum that filled all space, a medium through which all motion passed. For nearly 2,000 years, this belief shaped the world's understanding. The void, if it existed at all, was a flaw in nature's design. And yet, whispers of the opposite would occasionally arise. Strange observations in the heavens, anomalies in the flow of air and water, hints that perhaps nothingness could be real. By the 17th century, the pendulum began to swing. Galileo's experiments with falling bodies, and later Evangelista Torricelli's creation of the first mercury barometer, revealed something startling. When air was removed, nature did not rush to collapse the space completely. A bubble of emptiness could be created, and it could persist. Blaise Pascal carried Torricelli's tubes up a mountain, proving that the ocean of air above our heads was finite, that there could indeed be a place without matter. Isaac Newton would later frame this new reality in the vast, rigid terms of absolute space, an invisible, unchanging stage upon which the universe played. Here, the vacuum was no longer heresy, but foundation. Still, it was thought to be truly empty, a pristine nothing in which celestial bodies moved. But even this was not the final word. By the 19th century, the rise of electromagnetism introduced a new puzzle. Light, like sound, was assumed to need a medium to travel through. Scientists proposed the luminiferous ether, an invisible substance pervading the vacuum, carrying electromagnetic waves the way air carries sound. It was a compromise, a way to keep the void, but also keep it full. For decades, physicists tried to detect this ether, designing ever more delicate experiments to reveal its presence. The turning point came in 1887, with the Michelson-Morley experiment. Two American physicists built one of the most precise instruments of their age, hoping to measure Earth's motion through the ether. The result was silence. No shift, no drift, no sign of a medium. The ether was not there. Space, it seemed, might truly be empty after all, and yet this emptiness would not remain simple. The 20th century brought the quantum revolution, a storm that tore apart the classical stage. Max Planck's discovery of the quantum nature of energy hinted that even the smallest units of light and heat behaved in discrete, indivisible packets. Albert Einstein expanded the vision. Space and time were not rigid, but dynamic, bending and stretching in response to energy and matter. The stage could ripple. The void could move. Then came Paul Dirac, whose equations hinted at a deeper truth, that every particle must have a mirror image, an antiparticle. In his formulation, the vacuum was not barren at all, but a sea, a Dirac sea, filled with invisible states where absence itself could behave like presence. This idea, strange and abstract, planted a seed that would grow into the modern concept of quantum fields. The first tangible cracks in the illusion of emptiness came in the mid-20th century. In 1947, Willis Lamb and Robert Rutherford measured a tiny shift in the energy levels of hydrogen atoms, a shift that could only be explained if the vacuum itself was subtly altering the space around the electron. The same year, the effect emerged from the mind of Hendrik Casimir. To uncharged metal plates, placed close together in a vacuum, would feel a mysterious force pushing them together. The explanation was astonishing. The plates were excluding certain quantum fluctuations of the vacuum between them, creating a pressure from the empty space outside. These were not philosophical arguments, nor fragile inferences. They were experiments, reproducible and precise. The perfect vacuum was revealing itself to be something far stranger than Newton's static void. For scientists raised on the comfort of a stage-like universe, this was a revelation tinged with unease. If the vacuum had energy, if it could push, pull, and shift the behavior of particles, then it was no longer a passive nothing. It was active, dynamic, perhaps even unstable. The shock was philosophical as much as scientific. What does it mean when nothing can act? When emptiness is not a backdrop, but a participant? By the close of the 20th century, the old image of the vacuum had been dismantled entirely. The ether was gone, absolute space was gone, and with them the last illusions of a pure, lifeless nothing. In their place stood a new vision, the quantum vacuum, a restless sea whose surface we barely understood. The road from Aristotle's abhorrence to Casimir's pressure had taken over to millennia, but it had brought us to a threshold. Ahead lay questions not about whether the vacuum was empty, but about what filled it, and whether that something could hold the key to the fate of the universe itself. It was here, standing at the edge of this new understanding, that science would confront its next shock. The realization that the vacuum's energy was not just a laboratory curiosity, but the most profound, and perhaps the most dangerous, force in all of reality. The turning point came quietly, not with a cataclysm in the heavens, but with numbers, the quiet, insistent voice of mathematics, whispering that the vacuum was not what it seemed. By the mid-20th century, quantum field theory had taken root. It was a strange, unsettling picture of reality, not a world of solid particles floating in emptiness, but an ocean of invisible fields stretching through all of space. Particles were not objects so much as ripples, brief excitations in a deeper fabric, and here was the most unsettling part. Even when no ripples were present, the fields themselves were not still. They trembled, they fluctuated, they hummed with a low, constant energy. This was the zero-point energy, the inescapable residue of motion and vibration, even at absolute zero. No matter how thoroughly space was drained of matter, stripped of photons, cooled beyond the reach of any thermal heat, the vacuum still carried energy. It was as if reality could never fully stop moving. In the abstract language of quantum mechanics, this made sense. Heisenberg's uncertainty principle dictated that energy and time were intertwined. The more precisely one knew the energy in a system, the less precisely one could know its duration. For the vacuum, this meant energy could momentarily appear from nowhere, so long as it vanished quickly enough. The universe, it seemed, was forever lending and reclaiming from itself. Physicists called these ephemeral bursts virtual particles. In the shadowed depths of the vacuum, they appeared and disappeared endlessly, colliding, annihilating, exchanging momentum, all within the tight constraints of quantum law. They were unobservable directly, but their fingerprints could be seen in the Casimir effect, in the Lamb shift, and in the scattering patterns of high-energy experiments. And then came the real shock. If quantum field theory was correct, the total zero-point energy of the vacuum should be enormous. Every quantum field, of which there were many, contributed to it. Adding up these contributions across all possible frequencies, the numbers spiraled to an almost absurd scale. How absurd? Enough energy in a single cubic centimeter of vacuum to boil every ocean on Earth. Enough to curve space so violently that the universe should have curled back in on itself instantly after the Big Bang. Yet, this had not happened. The stars shone in peaceful arcs. Galaxies drifted in quiet expansion. The universe endured. This became known as the cosmological constant problem, one of the deepest and most embarrassing gaps in physics. The vacuum energy, predicted by quantum theory, overshot what astronomers observed by 120 orders of magnitude. No other mismatch between theory and reality in the history of science had ever been so extreme. Here, the story circled back to Albert Einstein. In 1917, he had introduced a cosmological constant into his equations of general relativity, a fudge factor to hold the universe static against the pull of gravity. When Edwin Hubble later discovered that the universe was expanding, Einstein abandoned the constant, calling it his greatest blunder. But now, decades later, it returned in an unexpected form. Observations in the late 20th century revealed that not only was the universe expanding, it was accelerating. Something in the vacuum itself was pushing space apart. Astronomers began to speak of dark energy, an invisible pressure pervading all of space, behaving exactly like a small but non-zero cosmological constant. In other words, the vacuum's energy was real, measurable, and shaping the cosmos. The shock was complete. The nothingness between the stars was not passive. It was dynamic, exerting a force on the largest possible scales. The very geometry of the universe was being rewritten by something no eye could see. The implications were staggering. If the vacuum had energy, it could, in principle, be tapped, a limitless reservoir waiting to be harnessed. Science fiction seized the idea, imagining ships propelled by quantum fluctuations, cities powered by the void itself. But the practical barriers were immense. The vacuum's energy was not a pool one could simply siphon from. It was bound into the structure of reality, accessible only through effects so subtle that measuring them was itself a triumph. For the scientists confronting this new reality, The emotional response was twofold. There was wonder, the awe of discovering that what had once been dismissed as nothing was, in fact, the most fundamental something. But there was also unease. If the vacuum could drive the expansion of the universe, could it also destroy it? Theoretical physicists began to imagine unsettling possibilities. What if the vacuum we inhabit is not the lowest possible energy state? What if it is metastable, a precarious plateau in a deeper landscape of possible vacua? A sufficiently energetic event, perhaps a collision of cosmic rays or the birth of a black hole, could push the vacuum over the edge into a lower state. In an instant, the laws of physics could change, and a wave of destruction could sweep outward at the speed of light. No warning, no resistance. This was not science fiction. It was a sober calculation derived from quantum field theory. Stephen Hawking himself spoke of such risks, noting that experiments probing the Higgs field might someday brush against dangerous thresholds. Others cautioned that nature had already tested these limits in cosmic collisions far more powerful than anything on Earth and the universe had survived. But the shadow of the possibility remained. The vacuum was no longer a stage. It was a character, powerful, unpredictable, and possibly unstable. From Aristotle's abhorrence to Newton's absolute space, from ether to quantum sea, humanity had come to see nothingness as a mirror of its own ignorance, a placeholder for what it did not yet understand. Now, the mirror was breaking in its fragments. The picture that emerged was stranger than anyone had expected. The vacuum was not absence. It was the foundation stone of reality, the silent engine that powered the expansion of the universe, sculpted the geometry of space-time, and whispered the rules by which particles were born and destroyed. But the more we understood, the less it felt secure. And so, the scientific journey pressed on deeper into the void, toward instruments and experiments that could measure the invisible, and perhaps reveal whether the vacuum was friend or executioner. The mystery of the vacuum could not remain in the realm of theory. Numbers and equations had shown its strangeness, but now instruments would have to face it directly, not in metaphors, not in mathematical limits, but in measurable effects. For the first time in human history, the technology existed to probe nothingness. In the vast caverns of particle accelerators, scientists began creating pockets of almost perfect emptiness. Chambers were drained of air to pressures trillions of times, lower than the atmosphere, colder than interstellar space, shielded from stray radiation. Inside them, beams of particles were hurled together at near-light speeds, their collisions producing not only showers of matter, but something more elusive, signs of the vacuum itself at work, quantum electrodynamics, the theory describing the interaction of light and matter, predicted that the vacuum could polarize under extreme conditions. Like glass bending light, the vacuum could bend the paths of photons. The effect was subtle, but in the flicker of data from high-energy collisions, there were hints of this bending, a ghostly signature of the vacuum's invisible fields responding. To the chaos in such collisions, pairs of particles and antiparticles would sometimes emerge from nowhere. Electron-positron twins, born together, annihilating in flashes of light. They were not pulled from any nearby atom. They came from the vacuum itself, coaxed into existence by the energy of the collision. It was a glimpse into the ceaseless churn of the quantum sea, a process happening everywhere, all the time. Beyond the reach of our senses, above Earth, satellites joined the search. The cosmic microwave background, the faint afterglow of the Big Bang, became a map of the early vacuum. Minute temperature variations, measured by missions like COBE, WMAP, and Planck, revealed the fingerprints of quantum fluctuations stretched across the sky. These were not random specks of noise. They were the amplified echoes of the vacuum's restless energy in the universe's first moments. In the cold stillness of space, the vacuum had not been a passive backdrop. It had seeded the structure of everything to come: the galaxies, the stars, the planets. All of them emerged from patterns written in the foam of the early vacuum. The quest reached into realms of theory once thought untestable. Physicists explored the Unruh effect, a phenomenon predicted but not yet observed, that an accelerating observer, even in perfect vacuum, would perceive a warm glow, a bath of particles emerging from the void. It suggested that the vacuum was not absolute but relative. To one observer, empty; to another, filled with heat. Even more startling was Hawking radiation, the process by which black holes could slowly evaporate. At their event horizons, the vacuum seethed with particle pairs. Normally, these pairs would annihilate and vanish back into nothing, but if one particle fell into the black hole while the other escaped, the vacuum's fluctuation would become real. The black hole would lose a tiny fraction of its mass, and the escaped particle would carry energy into the cosmos over unimaginable timescales. The vacuum could undo even the most extreme objects in nature. Back on Earth, the Casimir effect remained one of the most elegant and unsettling proofs that the vacuum was active. In laboratories, to perfectly smooth metal plates, placed nanometers apart in an ultra-clean vacuum, would drift toward each other. No force could be measured between them from charge or magnetism, and yet they moved. The reason lay in the spectrum of quantum fluctuations. Between the plates, only certain wavelengths could exist. Outside them, all wavelengths were allowed. The imbalance in vacuum pressure pushed the plates together, as if emptiness itself were exerting a hand. These experiments required a level of precision bordering on the absurd control of surfaces. At the atomic level, elimination of stray vibrations, shielding from the faintest whiff of heat. And yet, again and again, they confirmed the same truth. The vacuum is not empty, and its influence can be felt. On cosmic scales, telescopes observed an even more profound effect. When astronomers measured the motion of galaxies in the late 1990s, using distant supernovae as cosmic mile markers, they found the universe's expansion was accelerating. The culprit was not visible matter, nor dark matter, but a uniform energy pervading all space, consistent with the vacuum energy predicted by quantum theory, though at a much smaller magnitude than the equations had suggested. This was the dark energy already whispered about in theoretical discussions, now written into observation. It was as if the vacuum was stretching space from within, a quiet pressure that grew more dominant as the cosmos expanded and matter thinned out. In the far future, if this expansion continues, galaxies will drift beyond each other's light, and the universe will fade into an isolation shaped entirely by the vacuum's hand. The picture that emerged from these investigations was one of layered complexity. On the smallest scales, the vacuum boiled with virtual particles. On the largest, it shaped the destiny of the cosmos. And between these extremes, it bent light, altered forces, and defined the very constants of nature. Yet, every discovery deepened the mystery. Why does the vacuum have the energy it does? Neither zero nor the catastrophic infinity predicted by theory. Is its value constant, or will it change over cosmic time? Are we living in a stable vacuum, or on a precarious plateau in a deeper energy landscape. In pursuit of answers, science built tools at the very edge of feasibility. Lasers split light into exquisite pulses to probe minute changes in vacuum polarization. Atomic clocks measured time so precisely they could detect tiny shifts in space-time itself, searching for hints of new vacuum effects. Deep in Antarctic ice, neutrino detectors waited for ghostly particles born from vacuum interactions in the depths of space. The deeper the investigation went, the more the vacuum appeared, not as a passive emptiness, but as the foundation upon which all else is built, a restless, invisible engine that never sleeps. And somewhere within this engine may lie the key to the universe's birth and its death. The deeper science peered into the vacuum, the more its calm facade began to fracture. What had begun as a subtle hum beneath reality now revealed hints of danger. The suggestion that this invisible foundation might be fragile, that the stage upon which the universe stood could, under the right conditions, give way entirely. It was Stephen Hawking who, in the late 20th century, spoke openly of one of the most unsettling possibilities: vacuum instability. The Higgs field, the quantum field, responsible for giving particles their mass, might not be in its most stable state. Instead, it could be in what physicists call a false vacuum, a local minimum of energy rather than the true lowest point. Imagine a marble resting in a shallow dent high on the slope of a hill. It appears stable, but only because it has not yet been nudged over the edge. A single push, a fluctuation large enough, could send it rolling down into the valley below. In the case of the universe, that valley would be a deeper, more stable vacuum state, and the transition would be catastrophic if such a collapse were triggered. The laws of physics themselves could change in an instant. The constants that shape chemistry, the forces that hold atoms together, even the speed of light might be rewritten. Every structure, from galaxies to cells, would be unmade, and there would be no warning. The transformation would race outward. At the speed of light, a silent shockwave of annihilation, giving no time for escape, not even for thought. The cause of such a trigger is unknown. It could arise naturally from quantum fluctuations, random, inevitable consequences of the uncertainty that governs the smallest scales, or it could be provoked by extreme events, collisions of ultra-high energy, cosmic rays, the collapse of massive stars, or, in theory, experiments probing energies close to those of the early universe. Most physicists believe nature has already tested these extremes countless times in cosmic history. Black holes have collided, quasars have flared, particles of unimaginable energy have struck the Earth, and still the vacuum has held. Yet the possibility, however remote, lingers like a shadow at the edge of every theory. Beyond the threat of collapse lies another, more subtle escalation: the vacuum's role in the accelerating expansion of the universe. In the late 1990s, when two independent teams measured distant type Ia supernova to map cosmic expansion, they expected to find that gravity was slowing the universe's growth. Instead, they found the opposite. The expansion was speeding up, pushed, it seemed, by an invisible pressure woven into space itself. This force was identified as dark energy, and the simplest explanation for it was the energy of the vacuum. But unlike a static cosmological constant, some theories suggest this energy could change over time. If it grows, even slowly, the acceleration will increase, stretching the universe faster and faster until, in a distant future, galaxies will slip beyond one another's reach. stars will burn out, and the cosmos will enter a state of eternal isolation. Other models paint an even stranger picture, a phantom energy scenario, where the vacuum's repulsive force becomes so strong that it eventually tears apart galaxies, then stars, then atoms themselves, a big rip, ending the universe in a final shattering of space-time. These visions, the false vacuum collapse, the big rip, are not predictions in the ordinary sense. They are possibilities derived from the mathematics of quantum fields and general relativity, consistent with current observations, yet beyond the power of our experiments to confirm or refute. They are reminders that the vacuum, for all its apparent stability, is not bound to our expectations in the story of the cosmos. The vacuum may not simply be a background presence. It may be the driver of the plot, the hidden engine that began the first act, and will write the last dot. Evidence for this active role comes from the earliest moments after the Big Bang. Inflationary cosmology, developed in the 1980s, proposes that in the first fraction of a second, the universe underwent a period of exponential expansion, driven by a high-energy vacuum-like state. This inflation would have stretched quantum fluctuations into macroscopic seeds, later growing into the galaxies and clusters we see today. If this theory is correct, the vacuum is not just the quiet custodian of the present universe, it was the architect of its birth. And in the broader framework of some models, inflation never truly ends. In far-off regions, it continues eternally, spawning new bubble universes with different vacuum states, each with its own physical laws. This multiverse vision is speculative, but it emerges naturally from the mathematics of inflation and quantum field theory. If the vacuum can exist in multiple forms, then perhaps our own is just one island in a vast ocean of possibilities, and its stability, far from guaranteed, may be temporary. For many scientists, this deepens the mystery, rather than resolves it. If there are countless possible vacuum states, why are we in this one? Did it arise by chance? Or is there some deeper principle, an as-yet unseen rule that selects vacua, capable of giving rise to complex structures like galaxies, planets, and life? These are not questions of idle curiosity. They strike at the heart of why the universe is the way it is, and whether it can remain so. If the vacuum is unstable, then the clock is ticking, perhaps for trillions of years, perhaps until the next quantum heartbeat. The escalation of the vacuum mystery is not just a rise in scientific stakes, it is a shift in perspective. It forces us to see the void not as a passive nothingness, but as a volatile field whose moods shape the fate of everything. It reminds us that the ground beneath reality is not solid, but may be trembling imperceptibly, invisibly, yet in ways that could decide the destiny of all that exists. From here, the path leads inevitably into theory, into the possible explanations, the competing models, and the speculative landscapes that seek to tame this dangerous emptiness. But even before we take that step, the vacuum has already shown itself to be more than a scientific curiosity. It is a reminder of the fragility of existence, a whisper in the silence between stars that says, the void is not empty, and it is not safe. When faced with a mystery that touches the birth, life, and death of the universe, science does what it has always done. It builds models. These models are not guesses in the casual sense. They are architectures of mathematics, each rooted in what is known, each stretching toward what might be true. For the vacuum, the central question is simple yet profound. What is it? And from this question, a spectrum of theories unfolds. The most widely accepted framework is quantum field theory. The idea that every particle in existence is an excitation of an underlying field. These fields fill all of space, whether or not particles are present. The electron field, the quark fields, the photon field, each one is always there, silent unless disturbed. In this view, the vacuum is the ground state of all these fields. But the ground state is not truly still. Thanks to the uncertainty principle, each field trembles with zero-point energy, producing fleeting particles and antiparticles in an endless cycle of creation and annihilation. What we call empty space is actually a restless ocean of quantum foam, yet even this elegant picture has gaps. If the vacuum is just the sum of all ground states, why is its measured energy density so small? Why does it drive cosmic expansion at the observed gentle rate rather than the catastrophic pace predicted by calculations? This is the cosmological constant problem, unsolved and unforgiving, a reminder that even our best theory may be incomplete. Some physicists believe the solution lies in the multiverse. If space can take on many possible vacuum states, each with its own energy level and physical laws, then perhaps our universe is one bubble in a vast inflating sea. In this string theory landscape scenario, there could be 10500, 10500, 10500, or more possible most would be inhospitable, too much vacuum energy, and space would rip apart before matter could form. Too little, and the universe would collapse before stars could ignite. Our vacuum might be one of the rare, stable states where complex structures can emerge, a cosmic accident, observed only because it is one of the few where observers are possible at all. This reasoning, called the anthropic principle, is controversial. To some, it feels like surrender, an admission that the vacuum's properties are not dictated by a deeper law, but by cosmic lottery. To others, it is a natural consequence of a vast multiverse, where every possibility exists somewhere. Other approaches search for the missing law. Some propose that the vacuum energy is dynamically regulated, not fixed, but slowly adjusting towards zero through unknown processes. These ideas fall under quintessence models, where a slowly evolving scalar field permeates the universe, changing its influence over time. In such scenarios, dark energy might not be constant. The cosmic acceleration we observe today could be temporary, even reversible. Then there is the radical possibility that the vacuum's structure is tied to quantum gravity, the still elusive theory that would unify general relativity with quantum mechanics. In this realm, space-time itself might be granular at the smallest scales, with the vacuum emerging from the collective behavior of microscopic atoms of space. If true, what we call empty space would be as real and structured as a crystal lattice, invisible at human scales, but fundamental nonetheless. Even within accepted theory, the vacuum is an active player in shaping matter. Vacuum fluctuations can give rise to real, lasting phenomena. In the early universe, during inflation, quantum ripples in the vacuum were stretched across cosmic scales, becoming the seeds of galaxies. The very pattern of the night sky is, in this sense, a fossil record of the vacuum's restless heart. Some speculative proposals push further, asking whether these fluctuations could be harnessed. Zero-point energy has been invoked in science fiction as a limitless power source, a way to tap the fabric of space for propulsion or civilization-scale energy. In reality, extracting usable energy from the vacuum is fraught with paradoxes. The fluctuations are symmetric. Any local gain would be cancelled by an equal loss. Attempts to disturb the vacuum enough to yield net energy would likely require more energy than they produce. Still, the dream persists. The Casimir effect proves that vacuum fluctuations can exert measurable forces. Theoretical constructs, like the Alcubierre warp drive, imagine using regions of altered vacuum energy to contract and expand spacetime, allowing faster-than-light travel without violating relativity. These ideas remain purely theoretical, dependent on energy densities and engineering far beyond current capability, but they are reminders of how intimately the vacuum is tied to the shape of space and time. Perhaps the most unsettling speculation remains the one we cannot fully test: vacuum decay. If our vacuum is metastable, then somewhere in the vastness of space, a bubble of lower energy vacuum could form. Inside this bubble, the laws of physics would be different. Outside it, our universe would continue unchanged until the bubble expanded at light speed, consuming everything. Quantum tunneling, the same process that allows particles to cross barriers they should not, could trigger such a transition at any moment. The mathematics of quantum field theory allows this possibility, but the probabilities are so small that the universe's expected lifetime stretches far beyond any human timescale. Still, the thought lingers. The vacuum is not a fortress. It is a balance. All of these theories, quantum fields, multiverse landscapes, quintessence, quantum gravity, point toward a common truth. The vacuum is not a passive emptiness. It is a physical state, shaped by laws we do not fully know, capable of changing, perhaps of ending, and in the quiet of space, between the galaxies, in the depths of black holes, and in the first fractions of a second after the Big Bang, the vacuum has left clues to its nature. The challenge is not only to find them, but to understand them before the story reaches its final chapter. For if the vacuum is the foundation, then to know it is to glimpse the blueprint of reality itself, and to change it, even in theory, would be to rewrite the universe. To study the vacuum is to study the stage upon which reality is written. But, unlike stars, galaxies, or particles, the vacuum does not shine, scatter light, or leave tracks. It is the canvas itself, and measuring it requires instruments of extraordinary subtlety. Today, science pushes the limits of engineering to confront this invisible presence. Every tool is an attempt to make the intangible tangible, to force the vacuum to reveal its fingerprints in ways we can record, measure, and verify. Beneath the Swiss-French border, the Large Hadron Collider hums in the darkness. Its 27-kilometer ring accelerates protons to within a fraction of the speed of light, smashing them together at energies that mimic conditions a trillionth of a second after the Big Bang. The collisions are not just about producing exotic particles. Like the Higgs boson, they are tests of the vacuum itself. The Higgs field, inseparable from the vacuum's structure, determines the masses of fundamental particles. By measuring the Higgs boson's properties with exquisite precision, physicists hope to determine whether our vacuum is stable, metastable, or perched dangerously close to instability. Every decimal of mass, every fraction of a decay rate, is a clue to whether the universe's foundation is permanent or poised for change in the silence of deep space. The James Webb Space Telescope listens to the faintest light from the earliest galaxies. Its infrared vision can pierce the veil of cosmic time, reaching back to when the first structures emerged from the vacuum's quantum ripples. By studying the shapes, distributions, and motions of these ancient objects, Webb may reveal how vacuum energy shaped the cosmos' earliest expansion, and whether its influence has changed over billions of years. Closer to home, laser interferometers instruments so precise they can measure distances smaller than a proton's width. Search 4-minute distortions in spacetime. These detectors, cousins to those that revealed gravitational waves, could in principle detect shifts in the vacuum's refractive index, caused by strong magnetic fields or passing high-energy particles. Atomic clocks represent another front. In the investigation, the most advanced clocks now lose or gain less than a second over the entire age of the universe. They are so sensitive that they can detect changes in time caused by moving a few centimeters higher in Earth's gravitational field. This precision opens a new possibility to detect slow drifts in the constants of nature, such as the fine structure constant, which could indicate that the vacuum's properties are evolving. If such a change were detected, it would signal that the vacuum is not fixed, but dynamic. Some experiments push into environments that mimic the extremes of the early universe. High-intensity laser facilities, like those in Europe and Japan, focus beams so powerful they can momentarily rival the energy density inside stars. When these beams intersect, they create electromagnetic fields strong enough to polarize the vacuum itself, a direct test of quantum electrodynamics under extreme conditions. Detecting the subtle scattering of light from these experiments would be a triumph, confirming predictions that have so far existed only on paper. In Antarctica, buried deep beneath the ice, the IceCube Neutrino Observatory waits for particles that pass through light years of matter without interacting. Neutrinos are ideal messengers for studying the vacuum. They travel unimpeded through vast cosmic distances, their properties subtly shaped by the fields they traverse. If the vacuum has exotic features, hidden dimensions, unknown particles, or irregularities in its energy density, they might leave faint imprints on these ghostly travelers. At the opposite scale, in the microgravity environment of the International Space Station, cold atom experiments trap clouds of atoms near absolute zero, letting them drift freely for seconds at a time. Here, without Earth's pull, quantum effects become clearer. These experiments aim to test whether vacuum fluctuations influence atomic motion in ways we have not yet seen, an attempt to catch the vacuum in the act, even in the quietest possible conditions. Yet, for all this precision, there is a limit. The vacuum is the baseline of everything, and probing it is like trying to measure the paper by examining the ink. Our tools interact with it indirectly through forces, particles, and fields, never touching it in isolation. Each experiment reveals only a fragment of its nature, and assembling these fragments into a full picture remains one of the hardest challenges in science. Still, progress is relentless. Proposed missions, like the Nancy Grace Roman Space Telescope, aim to map the large-scale structure of the universe with unprecedented detail, tracking the influence of dark energy and, by extension, vacuum energy over cosmic history. Projects like the Euclid mission, launched by the European Space Agency, will chart billions of galaxies to understand whether cosmic acceleration is truly constant or subtly changing. In laboratories, next-generation colliders are being designed to surpass the LHC, reaching energies where the vacuum's hidden structure might be forced into the open. Quantum sensors, still in their infancy, may one day detect the vacuum's fluctuations directly, without relying on indirect effects. All of this is done in pursuit of a deceptively simple question: is the vacuum a fixed foundation, or is it an active, evolving player in the universe's story? If it is fixed, our cosmos may expand quietly for trillions of years, fading slowly into darkness. If it is changing, The future could be far stranger, a universe where the rules themselves shift, reshaping reality in ways we cannot yet imagine. The vacuum's nature is not an academic puzzle alone. It is a question about the stability of the ground beneath existence. Every measurement, every new instrument, is a step toward knowing whether that ground will hold forever, or one day give way. Soon, science will turn from measurement to meaning, from the cold clarity of data to the warm, uneasy weight of what it implies for life, time, and the universe itself. In the beginning, there was the void, or so the story was once told, a clean nothing, an empty canvas upon which the universe was painted. But now, after centuries of watching, measuring, and imagining, that story is no longer enough. The perfect vacuum, once the symbol of absolute absence, has revealed itself to be the most persistent presence in all of existence. The vacuum is not a backdrop. It is the silent loom upon which the threads of reality are woven. Every particle, every atom, every star, every galaxy, all emerge from its restless weave. It cradles the laws of physics, shaping the way matter behaves and the way time flows. And yet, it is not fixed. Beneath its calm surface lies a tremor, a reminder that even the most fundamental structures may not last forever. For humanity, this is more than a scientific revelation. It is a philosophical turning point. The ground of being itself may not be eternal. What we think of as stable, the charge of the electron, the strength of gravity, the speed of light, could all be artifacts of the vacuum's current state. Artifacts that might vanish if the vacuum changes. We live, therefore, in a fragile interval. Our universe is a particular configuration of fields and constants, born from the vacuum's own choices, if choice can be the right word for a blind, impersonal sea of quantum fluctuations. This interval has lasted nearly 14 billion years, but physics offers no promise it will last forever. The thought is humbling. It reminds us that permanence is an illusion, not only for individuals, species, or planets, but for universes themselves. When ancient philosophers contemplated nothingness, they feared it as the absence of being. But the modern vision is stranger still. The void is not an end, but a force, a creator as well as a destroyer. In it, galaxies are seeded. In it, they will dissolve. In this light, the vacuum becomes almost a character in the human story. Not a benevolent guide, not a malevolent adversary, but something deeper, an indifferent foundation. It gives without intention, it can take without warning. It existed before matter, and it will persist after the last star has faded. Perhaps the most haunting truth is that we cannot step outside it. We are woven from it, carried within it, and bound to it in every instant of our existence. The air we breathe, the light we see, the atoms of our bodies all ride upon the unseen scaffolding of the vacuum. Even our thoughts are patterns in fields that live in its depth. And yet, there is beauty here. For all its indifference, the vacuum has given rise to complexity, to consciousness, to creatures who can look into the night sky and wonder what lies beyond. From a sea of quantum foam came stars, from stars came planets, from planets came life, and from life the ability to ask, why? The answer may never come in the form we expect. It may be hidden in mathematics too deep for human minds, or in dimensions forever beyond our reach. Or it may be that the vacuum simply is, without cause, without need for explanation. If so, then the value lies not in solving it, but in seeing it, in understanding that the most ordinary space between things is the most extraordinary thing of all. From a human perspective, the vacuum's vast timescales and energies can feel alien, almost oppressive. The idea that the universe could, without warning, shift into a new vacuum state, rewriting physics in a silent wave, is beyond the scale of fear. But perhaps this is a reminder that our lives, our civilizations, and even our species are temporary arrangements of matter. We do not endure because the universe is stable. We endure because, for now, it is stable enough. And in that enough lies the gift of time. Time to learn, to explore, to imagine. Time to turn the instruments of science upon the sky. To listen for the vacuum's subtle changes. To push our understanding further into the black. When the last experiments are done, when the last equations are written, what will remain is the same as it has always been, the quiet between the stars, the soft hum of the fields, the ceaseless flutter of virtual particles. The vacuum will outlast our questions, our answers, and our existence, but it will not be unchanged. For in knowing it, in shaping instruments to measure its whisper, in imagining what lies inside it, we have, in a way, altered it. Not in its physical form, but in its meaning. For us, the vacuum is no longer nothing. It is the most universal. Something we know, perhaps in the far future, when the stars have cooled and galaxies have slipped beyond the cosmic horizon, there will still be watchers, beings, machines, or something stranger still, tracing the patterns of the vacuum as it slowly writes the next act of the cosmos. Or perhaps there will be no watchers, only the vacuum itself, folding into whatever form it will take next. In either case, our time here will have been a spark, brief but bright in the great dark sea. And so the camera drifts outward, away from the planets and suns, away from the filaments of galaxies, into the deep black. There is no music here, only the low, eternal hum of the vacuum. A voice, quiet, reflective, almost a whisper. Perhaps the universe is not built on matter, nor on light, but on the restless dreams of the vacuum itself.